Hi dear all, welcome you all to the Brilliant group of institution. Here we are going to discuss the most important MCQ for the chapter Alcohols, Phenols and Ether, the second organic chapter in your grade 12. Okay, so this is the part 1 video which include around 50 questions. We will meet again with the part 2, again 50 questions. Okay, so we are going to the first question dear all. Let's start from question number 1. Alright, here we have the first question. Match the column 1 with the column 2. Mark the appropriate choice. You can see here the first column they given some common name and second column they given some their structure. So we have to match it. Okay. You know the catechol, resorcinol, paracresol and quinol all are the common name for different compound, organic compound, right? Anyway, let me give you a small theory behind that. If we consider the compounds like, this is what phenol. Let me take one more phenol. Okay, other phenol. Alright, so this is one of the category. Here we can see that the phenol is common in all systems. Let me place one more alcohol on the same benzene ring. Like here one alcohol, here one alcohol, here one alcohol. What is the major difference between them? In the first question, or the first compound, the alcohol is on phenol, the extra OH group is on the ortho position. Then other one in the meta position and here para position. It's having a common name. If it is in the ortho position, it is said to be catechol. Catechol. If it is on the meta position, it is said to be resorcinol. Resorcinol. And if it is on the para position, it is said to be hydroquinone. Hydroquinone, or it is said to be quinol. Quinol. Hydroquinone, or it is said to be quinol. These are the common names. Maybe they can ask you what is the IUPAC name of this compound. Yes or no? What we can say? We can say benzene 1,2 diol, benzene 1,3 diol, benzene 1,4 diol, etc. Let me tell you the other term is called cresol. What is the meaning of cresol? You may study that. Again, I am going to take phenol. Okay, different type of phenol. So here I am taking general compound as phenol. Okay, phenol. Let me substitute one other substance. What is the other substance? That is methyl group. If the methyl group is on meta position, if it is in first one ortho, then meta, here it is para. So the names are different. Generally, if the phenol which contain a methyl group, then it is called cresol. So here it is in ortho position, is called orthocresol. Here it is in meta position, therefore metacresol. And here it is para position, therefore paracresol. That's it. Okay, let's go to the answer. So catechol, where is catechol dear all? Catechol, this is catechol. A matching with the 2. A matching with the 2 options are there. Then another one, resorcinol. Resorcinol means OH and OH are meta. So this is the B1. Paracresol, cresol means OH and CH3 para. This is C. So what is the answer? A with the second one, B with the third one, C with the fourth one, and quinol is OH opposite B1, that is option A is the correct answer. Okay, so common name we have to know very well which is given in the NCERT textbook. Alright, let's go to the second question. The carbon-oxygen-carbon angle in ether is about. It's the beginning part of the chapter. You can see the bond angle which is clearly mentioned in NCERT textbook for alcohol and ether. Generally, let me take one alcohol. Let us discuss first of all alcohol. Then we can go to ether. In an alcohol, the bonding is alcohol containing carbon, oxygen, hydrogen bond. Yes or no? If you consider the compound methanol, CH3OH, methanol. Then ether for example, you can take it methoxymethane, CH3OCH3. What is the bond angle? That is carbon, oxygen, carbon. COC bond is there. So in alcohol, if you consider the alcohol case, alcohol bond angle is near 109 degree. Exactly it is around 108.9 degree, but 109 degree. But in ether, the bond angle is little greater. It is around 111.7 degree, 111.7 degree. You know, there are most commonly same species bend the geometry. You know that oxygen contain lone pair. How many lone pair? 2 lone pairs are there, right? Oxygen containing lone pair. All right. Now, why? Normal tetrahedral, tetrahedral normal bond angle, 109 degree, 28 minute, or we will call 109.5 degree, correct? So this is the normal tetrahedral bond angle with this shape, tetrahedral bond angle. This is also can be exist in tetrahedral geometry, but the shape is like just what a bend shape, right? Why? And the another question, in normal tetrahedral bond angle is 109 degree 28 minute. In alcohol, it is little lesser, 109 degree, but in ether, it is greater than tetrahedral bond angle. Why? What is the major difference here all? In alcohol, there is a methyl group and one hydrogen. But in ether group, there is a ethyl group, methyl, like alkyl groups are there. Alkyl groups are little bulky group. So when these alkyl group come closer, what will happen? They will repulse. So in order to avoid the repulsion or to maintain a very free state, this carbon-carbon bond angle just relax. So what is the meaning? Bond angle increases. So another question, in ether, why bond angle is little greater than alcohol? So what is the answer? There are two bulky group nearby the central oxygen. So in order to what we can say, relax, in order to avoid the repulsion, so they are maintaining little gap. So that is the bond angle increases. So let's come to the question, what is the carbon-oxygen-carbon angle in ether is about? Ether is exactly around 111.7 degree, but here almost a similar answer what we can suggest, that is 110 degree. Okay, next one. Same concept, different question. The carbon-oxygen-hydrogen bond angle in alcohol is slightly lesser. In alcohol, how much we discussed? 109 degree. It is slightly lesser than tetrahedral bond angle. What is tetrahedral bond angle? 109 degree, 28 minute. Okay. Whereas the carbon-oxygen-carbon bond angle in ether is slightly greater. How much we discussed? 111.7 degree. What is the reason we discussed? Ether, there are two bulky group on oxygen. In order to avoid the repulsion, there are bond angle increases. So what is the answer? Option A, repulsion between the two alkyl R group. Yes, right? Repulsion is the problem. Therefore, ether existing with a slightly greater bond angle. Next question, all of you. An alkene. What is the alkene? Propene. Okay, propene. CH3, CH double bond, CH2. Propene. Propene is treated with the B2H6 diborane. Diborane based only one equation we are studying in 12th grade, especially alcohol chapter. You may study now in the preparation of alcohol. First preparation from alkene. From alkene, once you prepare alcohol through addition of water in presence of acid hydrolysis, you study the mechanism, everything. This is the second method, same from alkene, that is called what? Hydroboration. Hydroboration. After that, oxidation. Hydroboration, oxidation. What is the meaning of hydroboration? Addition of hydrogen and boron. So we are selecting the compound diborane. What is diborane, dear all? I'm not writing the entire reaction, no need of that. This is the exact example given in textbook. What is this? Propene. Propone. Diborane. First we are adding diborane, B2H6. So let me add B2H6. So you will get a compound at the intermediate. After that, what is the second process? Oxidation. Oxidation, we will add hydrogen peroxide in water in presence of a OH minus medium. So this is what happening. First step is called hydroboration. Second step is called what? Oxidation. Very simple to write the product. Okay. So boron or diborane related only one question. The hydroboration, oxidation. Whatever the alkene given, you make their alcohol. Propene is given. So which one? So you have confusion whether I want to make propan 1-ol or propan 2-ol. Don't worry, it will give primary. So what is that? Propan 1-ol, CH3, CH2, CH2OH. Propan 1-ol will be the product. So propene is given. This is the only one example given in textbook. Propene is given. If you are doing hydroboration oxidation, your product will be propan 1-ol or propanol. So what is your answer? Option C. Okay, option C. In the preparation of alcohol, you can see the same example. Next one. Choose the correct compound X and Y in the following reaction. Dear all, let me just write the reaction. You can see that in the first compound, all of you look into the first compound. What are the functional group in the first compound? Can you identify? There are two functional group in the first compound. What are they? This is a ketone. This is a ketone. Is it a ketone, the other one? No, it is ester. COO is there. Right? This is a ester part. Okay. Similarly, what is in the second compound? What's the functional group you can identify? That is aldehyde. Correct? Yes, aldehyde. Okay. What is the reagent here all? NaBH4 sodium borohydride. You know, sodium borohydride is a reducing agent. What is the major purpose of NaBH4 reducing agent? It can convert ketones into, on reduction, you know, it will give you secondary alcohol. Aldehydes on reduction, it will give you primary alcohol. This is the major purpose of which one? NaBH4, that is called sodium borohydride. This is the major purpose. So you got the answer. You have a ketone and ester in the first compound. Don't disturb ester, okay? Don't touch on ester, because ester there is no reduction. Ester you cannot reduce by using NaBH4. Okay, NaBH4 only purpose ketone and aldehyde. So don't disturb your ester part. So what is your product? First you will get it. Ketone reducing, you will get secondary alcohol. So you make it that part alcohol. Okay, then this part no changes. CH2, COO, CH3. Ester, don't change it. What about the second part? You can see there is an aldehyde, right? Aldehyde on reduction, it will give you primary alcohol. So what we can write? CH3, CH2, CH3. Aldehyde on reduction, what you are getting? Primary alcohol. So CHO converted to CH2OH alcohol. So this is what the product. So can you identify this product anywhere? Option A, no. Option A, they didn't make any change on ketone. Option B, they reduced the ketone as well as ester. Don't touch ester. Option C, yeah, they reduced the ketone. They didn't touch ester part. Yeah, they reduced aldehyde. Correct. Option C is the correct answer. Okay, let's go to the next question. Which reducing agent is used for the following conversion? A carboxylic acid is given. You have to convert it to alcohol. You know the general trend of oxidation and reduction. You know, primary alcohols on oxidation, we will get always aldehyde. Aldehyde further oxidation, we will get you carboxylic acid, right? Carboxylic acids, you will get it. Similarly, secondary alcohol on oxidation, we will get ketone, right? Ketone on oxidation, you will get again carboxylic acid. What about tertiary alcohol? You know, tertiary alcohol will not undergo oxidation. What is the process here we want? Here we need acid, we want to convert into alcohol. Primary alcohol is given here. How we can convert a carboxylic acid into alcohol? You know, the forward reaction, all I explained is oxidation. So what is the backward reaction? Reduction. Correct, reduction. Here is not a simple reduction. You need a very strong reduction, because normally carboxylic acid on reduction, you will get aldehyde. Aldehyde further reduction only, you will get alcohol. Correct. But here you want to reduce carboxylic acid directly into primary alcohol. So what is the reducing agent? What are the common reducing agents we are using? Hydrogen in presence of nickel, platinum, palladium catalyst. Or we are using sodium borohydride, NaBH4, the previous question. And the strongest one is which one, dear student? Lithium aluminium hydride. You know that is the strongest reducing agent. So what we can do here? We can use the LiAlH4. Can we use KMnO4 and K2Cr2O7? No, they are the strongest oxidizing agent. Okay, lithium aluminium hydride is the strongest reducing agent. Fine. Next question. 1 mole of ethyl acetate. What is ethyl acetate? Ester. What is ethyl group? CH3 single bond CH2. What is meant by acetate? You know acetic acid, right? What is acetic acid? Ethanoic acid. Correct? Ethanoic acid. When it loses this hydrogen, it is said to be acetate. Acetate. So let me add this species here. CH2, CO, CH3. So this is with acetate. This the part is called ethyl. This part is called acetate. This is an ester. Okay. What they are doing here, dear all, they are treating with the excess of the strongest reducing agent, lithium aluminium hydride. Okay, lithium aluminium hydride. Dear all, ester reduction you may study. Ester on reduction you will get 2 alcohol. Keep in mind, ester on reduction you will get 2 alcohol. How? Let's see. Very simple way you can understand like this. You just break this carbon oxygen bond. Okay, just to break the carbon oxygen bond. How many how many carbons are present the left side? You can see 2 carbon. What is a 2 carbon containing alcohol? Come on, what is a 2 carbon containing alcohol? Ethanol. Okay, plus. I told you ester on reduction you will get 2 alcohol. How many carbon present right side? Right side also there are 2 carbon atom. What is the 2 carbon containing alcohol? That's again ethanol. Okay, so whatever the ester given, just to break the CO bond, left how many carbon, right how many carbon, make it their alcohol. That's it. So what is your answer here all? You will get, this is ethanol, ethanol. Both are same product, right? Yes, you will get 2 moles of ethyl alcohol or ethanol. Okay, next question. Tertiary butyl alcohol can be prepared by the reaction of, let me tell you the theory, very important point. You know that Grignard reagent, right? Alkyl magnesium halide. Grignard reagent you can treat it with the aldehyde, ketone. You can prepare different type of alcohols, primary, secondary, tertiary, everything. Before doing the experiment, you can predict whether it is primary, secondary, tertiary, which is going to form. Very easy. Grignard reagent, when you treat it with the HCHO, what is meant by HCHO? The first aldehyde. What is this aldehyde called? Methanol, or what we can say formaldehyde, right? Formaldehyde. When you treat any Grignard reagent with methanol, you know, first you will get an intermediate, then you will add water in acid hydrolysis, everything. I'm writing the final product. Any Grignard reagent, when you treat it with methanol aldehyde, your product is confirmed, that is primary alcohol. Second one, any Grignard reagent, when you treat it with the other aldehyde, what? Other aldehyde except methanol. Okay, except, I'm underlining the term, except methanol. Except methanol. Except methanol. Methanol, if you use it, your product is fixed primary alcohol. But ethanol, if you are ethanol, propanol, butanol, any other aldehyde, if you are using, your product is different, it will be a secondary alcohol. Then what about tertiary? Grignard reagent, when you treat it with any ketone, you can prepare tertiary alcohol. Tertiary alcohol. It's a common I am saying, okay? Tertiary alcohol you can prepare. Let's go here. Tertiary butyl alcohol we want to prepare. They already said your alcohol is tertiary. What is tertiary butyl alcohol, dear all? This is the compound terbutyl with the alcohol. This alcohol you want to prepare. It is a tertiary alcohol, right? If you want to prepare tertiary alcohol, what is the condition? Grignard reagent should react with a ketone. Okay, where you can identify that? Option A, acetaldehyde treating with the ethyl magnesium iodide Grignard reagent. Possible? No. It is an aldehyde, right? So not our answer. Acetone. What is acetone? Propanol. Okay, what is acetone? Propanol. CH3CO, CH3, propanol. Yeah. Propanol treating with which one? Methyl magnesium iodide. Methyl magnesium iodide. Yeah. Here you can see this is a ketone, this is a Grignard reagent. Yes, you will get a tertiary alcohol. Can be an answer. Option C, formaldehyde. No. Formaldehyde, if you are using, always you will get primary alcohol. What about the other one? Butanol. What is butanol? It's a ketone, right? Butan 2-on or butanol. Alright, it is reacting with which one? Methyl magnesium iodide. Methyl magnesium iodide. So confusion. Option B is there, option D is there with the ketone. Which ketone can be selected? Very simple. All of you look into your product. In your product total, how many carbons are there? 1, 2, 3, 4. Total, correct. So you see the reactant side, how many total carbons are there in the second option? 1, 2, 3, 4. Yes, this is the product. What about option D? 1, 2, 3, 4, 5 carbons are there in your total product. You will get it if you perform D experiment. So option B is the correct answer. Okay, next. Propanol, again the same question. Propanol, what is propanol? I said CH3COCH3. Propanol on reaction with a alkyl magnesium bromide, which will give you after hydrolysis. What's that? I told you. Alkyl magnesium bromide. What is that? Grignard reagent. It's a ketone, right? Propanol. Propanol, when reacting with a ketone, when reacting with a Grignard reagent, your product is confirmed. It is tertiary alcohol. Let me show you once again. This is propanol, right? This is propanol. Let me take as any Grignard reagent. For example, CH3MgCl, methyl magnesium chloride. You know, in Grignard reagent, magnesium is the positive one, right? It's a metal atom. So CH3 is the negative one. It is the nucleophile. Nucleophile will come and attack to this carbon and it become O-. So what is the product? You are getting CH3, CCH3 and here CH3. Here we are getting O-. To this O- what will attack? This Mg plus Cl will attack. Not over. Process is not over. After that what? Hydrolysis. Okay, let me add water. Hydrolysis in presence of acid. Therefore it is called acid hydrolysis. You know, water contain 2 ions. What are they? H plus and OH-. You please add these ion into the above ion because this is O- and Mg plus. To the O- part you add H plus. To the Mg plus part you can add OH-. So what is the major product, all of you? CH3, CCH3, CH3. Here what it become? OH. Check it. It is a tertiary alcohol. Okay, so there is no need to practice this mechanism, no need to study. We can follow the previous rule which I said. Okay, 1, 2, 3. So here is a ketone treating with the Grignard reagent. Tertiary alcohol is the product. Option C. Next one. In the following sequence of reaction, what is the reaction, dear all? You have benzene. Okay, benzene. Benzene treating with the what? Oleum. What is oleum chemically? You know, fuming sulfuric acid, right? Oleum is what? You studied in P block chapter also, right? The oxo acids of which one? Sulfur. Oleum is called what? The fuming sulfuric acid formula H2S2O7. Okay, whatever. Oleum sulfuric acid, when you treat it with the benzene, it will give you SO3H electrophile on benzene. This is called benzene sulfonic acid. Benzene sulfonic acid, then we are treating with the NaOH and then we are treating with an acid. You studied this preparation as the preparation of phenol. How to convert benzene into phenol? First treated with the oleum, then treated with the sodium hydroxide and H+. Total in this chapter, you have studied around 4 methods of preparation of which one? Phenol. I think first is from, as per NCERT order, first is from chlorobenzene, dose process. Second is from benzene. Third from aniline, diazotization, then warm water. And fourth one from cumene. Correct. So, in the following reaction, what is the final product Q? That is nothing but phenol. This is one of the method of preparation of phenol from benzene. Next one. Cumene on reaction with the oxygen followed by hydrolysis give. This is the last method of preparation of phenol. What is cumene, dear all? Very simple reaction. Cumene means benzene with a isopropyl group. What is isopropyl group? One CH group connected to two CH3 group is called isopropyl. So cumene is also known as isopropyl benzene. Isopropyl benzene. Okay. Now first I am going to add oxygen. How many oxygen atoms are there in a O2 molecule? 2 oxygen. You please add that 2 oxygen atom in between the carbon and hydrogen. Which carbon? This carbon and hydrogen. So I can write the product like this. Benzene, CH3, CH3, OOH. Just add the 2 oxygen atom in between that carbon and hydrogen. Oh, what is the name of this product you studied? Cumene hydroperoxide. Cumene hydroperoxide. Why peroxide? You know, oxygen linkage is called peroxide linkage. Correct? But this is called cumene hydroperoxide. Now you have to do a small thing. Just treat it with the H3O plus. What is the meaning of H3O plus? Hydronium ion. How you are getting H3O plus? By addition of water in an acid. Right, or you can call it as H3O plus, simply mentioned in a arrow mean, which indicate that acid hydrolysis. Acid hydrolysis. Okay, you have to do a simple thing. You please take this OH group, only to remember, okay? Just to take the OH group, please attach directly on benzene ring. What is your product? Phenol. Alright, phenol. What is left in the system? You can see the left part is this one. What is that? That is a byproduct. CH3, one carbon, that carbon with an oxygen, double bond O, CH3. This is the product, byproduct. What is this byproduct? This is nothing but propanone, or we can say acetone. Right? Propanone or acetone. This is the method of preparation of phenol we studied from cumene. So, what is the final product, dear student? One is phenol, one is acetone. What is the option? Option D, C6H5OH phenol, CH3COCH3 acetone or propanol. Alright, next. Which of the following reaction will not yield a phenol? So I told you, total there are 4 methods. In textbook we studied for the preparation of phenol. 2 of them we already completed. I am not repeating. What are they? One is from cumene. Other one is from benzene. Let me write the other 2 things. First method, as in textbook we studied from chlorobenzene. This is chlorobenzene. How we can convert it into phenol. Chlorobenzene converted to phenol is known as Dawes process. What is Dawes process? Very simple. Chlorobenzene, first we are treating with the aqueous NaOH around 623 Kelvin, and what is the pressure? Remember, 300 atm pressure. What is happening here? This chlorine and hydrogen eliminated. ONA is substituted on benzene ring. What is benzene with the ONA is called sodium phenoxide. Sodium phenoxide. Now we want to cancel or remove the sodium, and we want to get a hydrogen. What we can treat? We can treat it with an acid like HCl. NaCl will eliminate, you will get phenol. This conversion is called Dawes process. Okay, what is so from benzene we prepared, from cumene we prepared, from chlorobenzene we prepared. Let me tell you what is the last one you remember? Aniline. So let me take aniline. What is aniline? Benzene with the NH2. Directly can you convert aniline into phenol? No. First to do diazotization. What is diazotization? NaNO2, sodium nitrite and HCl at 0 to 5 degrees Celsius. What is happening? Benzene diazonium chloride salt is forming, right? Benzene diaza means sulfur, nitrogen, diazonium chloride. And how you can convert benzene diazonium chloride into phenol? Simple, just to treat it with a warm water. Warm water. That's it. So these are the total 4 methods. Question which is not a preparation of phenol. First one is fine. Yeah. Chlorobenzene treating with the NaOH at 300 atm. Finally treating with the acid. Yeah, you will get phenol. Aniline, NaNO2 HCl diazotization, then warm water. Yeah, you will get it. Benzene, first we will treat it with the oleum, then NaOH and H+. Yeah, you will get it. Again, chlorobenzene, NaOH, but 1 atm. Is it a condition? No. Dose process 300 atm is the condition. This is the wrong one or the correct answer for the question. Alright, next. Which of the following statement is not correctly showing? Very careful, dear student, while answering the question, whether they mean which is correct or not correct. Okay, which is not correct statement. Option A, you can see the compound ethanol, propanol, butanol, they given solubility. Is it a correct order? Is it a correct order possible? Yes or no? Yes, because you know alcohols are highly soluble in water, no doubt, because they can make intermolecular hydrogen bonding with the water. All are alcohol, then what is the next parameter? We have to consider the number of carbon atom. You know, ethanol, propanol, butanol, while coming, there are number of carbon atoms are increasing. You know, carbons are non-polar species. They are not soluble in water. As the number of carbon increases, solubility decreases. So this is a correct statement. Option B, same species, they given in the opposite order, that is boiling point. Correct, right? Ethanol and propanol, when you consider propanol having greatest mass, and propanol and butanol, when you consider butanol having greatest mass, so what happened? Their boiling point increases. Correct one. Option C, propanol, and there is a branch. I think all are isomer. All are isomer, right? 3 carbon OH group, not isomer, right? Because it contains 4 carbon OH group. This is also 4 carbon OH group. They given in terms of boiling point. Correct or not? Yes. Why? You can say that there is a branch, right? It having branches. You know, as branching increases, boiling point decreases. And propanol contain only 3 carbon atom. Only 3 carbon atom. First factor we are considering for boiling point is mass. Propanol contain 3 carbon with OH group. Second one and this one and this one, which contain around 4 carbon. So definitely they having greater one. But among that, if you consider the branches, you know, branches, if you are discussing, they having greater the branching, lower will be the boiling point. So as per that, not exactly clear this one, not exactly the clear order, but as branching increases, you know, boiling point decreases. As per that, it's correct one. But what about option D? In option D, just a reverse order is given. This is the highly branched one, right? Highly branched one. This is boiling point order. They given the highly branched one having greatest boiling point. That is wrong. Correct. So this is the correct answer for our question. Option D. Next. Arrange the following compound in the increasing order of boiling point. What is the compound here? All propan 1-ol. Okay, let me take propan 1-ol. I'm not completely writing. Okay, propan 1-ol. Next one, butan 1-ol. Okay, 1, 2, 3, 4 with OH group. Another one, butan 2-ol. 1, 2, 3, 4. Second position alcohol. What is other one? Pentan 1-ol. Okay, pentan 1-ol. 5 carbon with alcohol. Before looking to the option, you tell me, dear student, which one having greatest boiling point? Boiling point, first factor determining the mass. Which one having greatest mass? Definitely pentan 1-ol. Correct, because they contain 5 carbon with 1 alcohol. What about among these 1, 2, 3 compound? Which one having greatest boiling point? No doubt, butan 1-ol, because the surface area greater, all carbons are in the straight chain. And the next one, so pentan 1-ol, then butan 1-ol. After that, which one? Propan 1-ol is there, butan 2-ol is there. Definitely butan 2-ol, even though there is a branch. Why? Because there are 4 carbon atom and 1 alcohol. Mass is greater. So then the least one is which one? This one, because mass is lesser. So pentan 1-ol greater, then butan 1-ol, then butan 2-ol, then propan 1-ol. That is option A. Alright? Next one. Orthonitrophenol. So many times we discuss many questions related to orthonitrophenol and para-nitrophenol. Orthonitrophenol is less soluble in water compared to para and meta-nitrophenol. What is the speciality in orthonitrophenol? You know, this is phenol, ortho position, there is a nitro group. You know that in orthonitrophenol there is a very weak force of this hydrogen and oxygen are connected through which one? It is a weak intramolecular hydrogen bonding. When a substance, we can say it is highly soluble in water when it can make a strong hydrogen bonding with the water. Orthonitrophenol, it's having a very weak type of bond. It cannot make the very strongest bond with the water. Therefore, their force of attraction will be, or solubility will be lesser. So, what is the answer? Option A, orthonitrophenol show intramolecular hydrogen bonding. Correct one. Orthonitrophenol show inter, not inter. Inter is in para. Correct. So orthonitrophenol showing very weak force of attraction, so its boiling point is less, or solubility is less. Next one. For the reaction, what's the reaction given? Ethanol, CH3, CH2OH. Ethanol treating with which compound, dear student? A hydrogen halide. For example, HCl something. Okay, HX. What you are getting? Definitely this OH and H eliminated. You will get X substituted. Right? CH3, CH2, X along with the water. Alright. What is the order of the reactivity of hydrogen halide? Even in P block also you studied what is the order. SN1 mechanism we studied, SN2 mechanism, P block chapter. Everywhere we are discussing about the reactivity order of hydrogen halide. If you consider HF, HCl, HBr, HI, down the group reactivity increases. Because fluorine is the most electronegative element, it's making very strong hydrogen bonding. Iodine is the biggest size and lower electronegative element, so this bond will be very weak. You can break this bond very fast, you can leave it for a reaction. So down the group reactivity increases in hydrogen halide. So what is the order? HI, HBr, HCl. Option B is the correct answer. Shall we go to the next one? Okay. Arrange the following alcohol in the order of increasing reactivity towards sodium metal. Sodium metal is given, alcohol is given. Okay. This reaction I can make into another sentence, like another question. Which of the following substance is most reactive towards sodium, or most acidic one? Sodium is a high, normally, if you are taking a alcohol CH3OH, if you treat it with a sodium, what will happen? Sodium is a highly reactive metal. It can displace hydrogen. Correct. So what you will get? CH3ONA plus hydrogen. What is its meaning? This compound donated a H plus ion. Donation of H plus ion is called what? Acidic character. So sodium, it is reacting faster, which meaning that it is highly acidic in nature. Okay, let's check it. The first compound is given terbutyl alcohol. Let me just elaborate. Terbutyl alcohol. Terbutyl alcohol. Second one is isopropyl alcohol. It is a secondary alcohol. It is a secondary alcohol. And third one is given ethanol. It is a primary alcohol. Okay, let me just note for your reference. This is a tertiary alcohol, it is a secondary alcohol, it is a primary alcohol. Okay, which is highly acidic in nature. What is the meaning of acidity? Its ability to lose H plus ion. Here you can see H plus ion is there, H plus ion is there, H plus ion is there. The main factor affecting acidity. Electron withdrawing group, if it is present, they will increase acidity. Electron donating group, if it is there, they will decrease acidity. Keep in mind. Electron withdrawing group can increase the acidity. Electron donating group will decrease the acidity. Which group is present in this compound? Alkyl groups. Alkyl groups are electron donating group. This is contained to alkyl group, donating group. It contains alkyl group, electron donating group. So what do you think? Which is more acidic? Which is more acidic? Primary, right? Because primary contain only less number of electron donating group. Normally electron donating group decrease the acidity. Option number 2 or compound number 2 and compound number 3 contain greater number of electron donating group. Electron donating group number increases, acidity again decreases. So what is the order, dear all? This one having more acidity. Third one, second one, first one. Third one, second one, first one. Yeah, Option C can be the answer. Okay, so keep in mind primary, tertiary, secondary alcohol when you consider primary alcohol having greater acidity. Next, out of 2-chloroethanol, let me just draw the compound 2-chloroethanol. What is ethanol? CH3CH2OH. Second carbon atom, let me place a chlorine. Okay, what is that? CH2Cl. Alright. 2-chloroethanol. And ethanol. Okay, let me take ethanol also. CH3CH2OH. Ethanol. Which is more acidic and why? What? Which is more acidic and why? What do you think? Which is more acidic? Or which compound is ready to leave hydrogen ion? Of course, the fact which I said in the previous question, electron withdrawing group, they will increase the acidity. Electron donating group, they will decrease the acidity. The only difference between these two compounds is the presence of extra presence of chlorine in the first compound. Chlorine, halogens are electron withdrawing group. Halogens are electron withdrawing group. So what will happen? Its acidity greater. What is the reason actually? Electron withdrawing group present, that is called minus I effect, minus inductive effect. Yes or no? Electron withdrawing groups are minus I groups, minus inductive effect group. Electron donating groups are plus I inductive effect group. So minus I effect or electron withdrawing group when comes, you can leave the hydrogen so easily. So what happened? What is the answer here on? Which is more acidic? 2-chloroethanol. What is the reason? Minus I effect, because chlorine is an electron withdrawing group. Option C is the correct answer. Hope you clear that. Let me go to the next question. What is the correct order of the strength of acidity? Dear all, alcohol chapter, acidity is a most expecting question. We can discuss maximum. The correct order of the strength of acidity of the following compound is, you know very well, phenol is highly acidic in nature, correct? Because when from phenol, if you remove this hydrogen atom as H plus ion, the whole existing compound is called what? Phenoxide ion. It is highly stable due to resonance. So the phenol is ready to leave hydrogen. It is highly acidic in nature. Unfortunately, here all compounds contain phenol. So let's go, no problem. They will give some other hint. Here you can see methyl group. Here you can see nitro group. Here there are 2 nitro groups. So what is the issue? Over. Methyl group is an electron donating group. Nitro group is a very strong electron withdrawing group. Okay? Nitro group is a very strong electron withdrawing group. So those who don't know what is electron donating and electron withdrawing, I will give you a list. Electron withdrawing groups are generally nitro group, cyanide group, aldehyde group, keto group, carboxylic acid, etc. Electron donating groups are methyl group, or generally all alkyl groups like methyl, ethyl, isopropyl, etc. and alkoxy group like methoxy, ethoxy, etc. And the common donating groups are, alcohol group, amine group, etc. Halogen in the normal aliphatic chain, they will act as an electron withdrawing group. On benzene ring, you know that it acts as a donating group when it is alone, right? Okay, come to the point. What is the major difference here, student? The major point we already learned, electron withdrawing group, if it is there, it will increase the acidity. It will increase the acidity. Electron donating group, if it is there, they will decrease the acidity. Correct or not? So let's go. Which one can show among this compound? Which one can show the best or which is the most acidic compound? Which is the most one? Definitely option the compound number 4, because it contains electron withdrawing group and 2 electron withdrawing groups are there. Fourth one, unfortunately, C and D both are 4 are there. Okay, no problem. After that, no doubt, third one, because it contains at least 1 electron withdrawing group. After that, which one? First one or second one? First one, correct. Because electron donating group will decrease the acidity. So compared to phenol, second one having least acidity. So 4, 3, 1, 2. 4, 3, 1, 2. That is option D is the correct answer. Okay, next. Para-nitrophenol is a stronger acid than. What is para-nitrophenol? Phenol This is para-nitro. Phenol they're saying it is a stronger acid than phenol. Okay, stronger acid than which one? Phenol. While paracrasol, do you remember what is paracrasol? Paracrasol means phenol and CH3. So para mean opposite. Paracrasol is a weaker acid than phenol. What is the reason? What is the reason? You know the reason, right? You know nitro group is a electron withdrawing group. Alkyl groups are electron donating group. That is the reason. So electron withdrawing group increase the acidity. Any answer is given? Option A. CH3 group decreases the electron density on oxygen of OH group, make paracrasol is a weaker acid. Is it correct? CH3 group decreases the electron density. No. Why? You know, if an electron donating group present, how acidity decreasing? This is an electron donating group, right? So they will donate maximum electron towards the benzene ring. Electron donating group will come, they will give maximum electron towards the benzene ring. So what happened? This OH bond, this oxygen and hydrogen, that bond gets stronger because they are giving electron. No. So the OH bond also getting electron, so they will become stronger. The hydrogen you cannot leave it faster. But what about electron withdrawing group present? If there is an electron withdrawing group present, they will try to pull the benzene containing electron all towards that. So what happened? This OH bond, this oxygen hydrogen bond containing electron density decreases. So this hydrogen you can easily donate as H plus ion, it becomes more acidic. So CH3 group decreases the electron density. No, it will increase. Option B, nitro group decreases the electron density on oxygen hydrogen bond, making para-nitrophenol. Yes, electron withdrawing group, they will decrease the electron density. Okay, next one. An unknown alcohol is treated with a Lucas reagent. You know, Lucas reagent is a mixture of concentrated hydrochloric acid with anhydrous zinc chloride. Lucas reagent to determine whether alcohol, you know, Lucas reagent test we are using to determine whether the alcohol is a primary, secondary or tertiary alcohol. Question: which alcohol react fastest and what mechanism? Let's see. You know the reaction with the Lucas reagent, right? Primary alcohol, secondary alcohol and tertiary alcohol. When you treat a primary, tertiary, secondary alcohol with the Lucas reagent, who will give most immediate reaction? You study tertiary. Correct. Tertiary will give you a immediate turbidity. It will give you a immediate turbidity. Because you know, tertiary alcohols are highly steric crowded one. They are ready to undergo some reaction, to leave something. Then what about secondary alcohol? It will give you turbidity only after 5 minutes, which means its reactivity little lesser compared to tertiary. What about primary? Under normal condition, they won't react with the Lucas reagent. Only by heating it can give some turbidity. So it can give turbidity only by heating, which means it is less reactive. So question, which is more reactive? No doubt, tertiary. Next confusion, whether it will follow SN1 or SN2 mechanism. You know, dear student, in haloalkane chapter, in part 1 and part 2 video, we detailed discuss about that. What is the order of SN1 mechanism? SN1 mechanism, the order is tertiary greater than, secondary greater than primary. Yes or no? Yes or no? SN1 mechanism. So tertiary alcohol will undergo which one? SN1. In SN2 mechanism, you know, primary undergoing faster. So answer is tertiary alcohol with the SN1 mechanism. Okay. Next, which of the following alcohol react most readily with the Lucas reagent? Please check it. Which is a tertiary alcohol? Option C, right? Option C is a tertiary alcohol. How we can identify primary, secondary, tertiary? Here OH connected carbon directly connected to only one carbon. Therefore, the first one is primary. Second one, the OH connected carbon directly connected to 2 carbon, therefore secondary. Third one, OH connected carbon directly connected to 3 carbon, tertiary. Here OH connected carbon directly connected to only 1 carbon, primary. So Lucas reagent test is greater in tertiary, therefore option C. Next one, dehydration of the following in increasing order is. What is meant by dehydration? Elimination of water. Let me give a simple example. I'm taking CH3, CH2OH. What is CH3, CH2OH? Ethanol. Normally for dehydration, we will use concentrated sulfuric acid like that. What we have to do during dehydration? Or from where we can eliminate water? Simple. Take your OH group from alpha carbon, take a hydrogen from beta carbon, eliminate water, make a double bond between alpha beta, finish. So your product will be a alkene, ethene with the water. Okay, once again, OH you have to take from alpha carbon, one hydrogen you take from beta carbon, make a double bond between alpha beta, finish. Here are, let me treat each compound with the acid. Let's make it a compound. Okay, first compound it is given clearly, that is phenol. First compound is phenol. Second compound is cyclohexanol, and third compound is cyclohexenol. Alkene is there with alcohol, and fourth one contain a diene in cyclohexane with alcohol. Question: which one can undergo dehydration faster? Dear all, it undergoing some reaction mean after the elimination of water, they should form a stable compound. Then only it is ready to leave water. Simply why they are not, why they are ready to leave water? No. If they remove water, the formed compound should be stable. Then only they will try to leave water. Correct? Okay. You see, let me just remove water from the first compound. Okay. You have to take from OH from alpha carbon, one hydrogen from beta carbon, make a double bond between alpha beta. It will be stable? No, because benzene is highly stable due to resonance. If you make one more double bond in the ring, it will be highly unstable, so they are not ready to undergo reaction. What about the second one? OH1 you have to, OH group you have to take from alpha carbon, one hydrogen you take from beta carbon, make a double bond between alpha beta, product is cyclohexene. What about the other cases, dear all? OH group you take from alpha carbon, one hydrogen you take from beta carbon, make a double bond between alpha beta, so I can get this product diene. Here OH I am taking from alpha carbon, hydrogen you can take from beta carbon, you can make the compound benzene. Now can you tell me which compound is ready to undergo the reaction? So after the elimination of water, which compound is highly stable? This one. Because it forming benzene, you know, benzene is highly stable due to resonance. Correct. After that, which one? Let's go with the third one. Because at least a small resonance is possible here. And what here? The first one, the second one. First one doesn't undergo because it is already it is a stable compound. After dehydration, it becomes unstable, not ready. So what is the order? 4, 3, 2, 1. This is the correct order of the reactivity. Answer is option A. Hope you clear the idea. Next one, dear. An alcohol acts on heating with a concentrator. So you have an alcohol, okay, you have an alcohol, they give an X, which is heating with a concentrated sulfuric acid, H2SO4. It is giving an alkene. Yes, definitely, because alcohol, when you heat it with the sulfuric acid, it will form dehydration, alkene, which can show geometrical isomerism. That is the master point. You know what is geometrical isomerism? Cis-trans isomerism. Correct. Let's see. Let me do with the first compound. What is the first compound? Option A, CH3, CH2, CH, OH, CH3. Butan 2-ol is the compound given. Let me remove water. Okay, concentrated sulfuric acid. Let me treat it. Dehydration. How you can perform dehydration? What I said? OH1 you have to take from alpha carbon, one hydrogen you take from beta carbon. Unfortunately, there are two beta, left one beta, right one beta. Which one we can select? The major product will be left beta. You have to take hydrogen according to Saints-of rule. According to Saints-of rule. What is Saints-of rule says that? More substituted alkenes are more stable. Maximum try to make the double bond at the center or the middle. That's a hint. Okay. So let me take this beta and this hydrogen. So after that you make a double bond between that alpha beta. But2-ene is the major product. Is this alkene can show geometrical isomerism? Yes. Let me take these two carbon atoms, C double bond C. First carbon contain one hydrogen and methyl group. So one hydrogen, one methyl group. Second carbon also contain one hydrogen, one methyl group. Let me place it like this. Which form is this? Cis form. Yes or no? Methyl, methyl, same side. Hydrogen, hydrogen, same side. So what is a trans form? If there is a cis, there will be a trans. Hydrogen, hydrogen opposite. Methyl, methyl opposite. It is said to be what? Trans form. Yes? Your answer is option A. Okay, dear all, option A is the correct answer. If you feel any doubt in this one, just to pause the video, just to read the question again, just to see the explanation, this one, the written one, and you can check it there whether it is correct or not. Okay, next. The most suitable reagent for the conversion of, I think it's given a primary alcohol, right? RCH2OH, it is a primary alcohol. You have to convert it into aldehyde. You know, primary alcohol, we studied primary alcohol. If you want to convert into aldehyde, the reaction is nothing but oxidation. What are the normal oxidizing agents we are using? PCC. What is pyridinium chlorochromate? Or we can use anhydrous CrO3. Or we can use copper at 573 Kelvin. All of them can be used for this conversion. Can we use K2Cr2O7? You know, that is potassium dichromate. It is a strong oxidizing agent. What's the problem if you're using a strong oxidizing agent? Not the problem. You know, aldehyde, further oxidation, we will get carboxylic acid. Correct? If you're using a strong oxidizing agent, primary alcohol, directly go to carboxylic acid. But we need only aldehyde. Up to that limit only required. So any of this is fine. K2Cr2O7, KMnO4 are strong oxidizing agent. Don't use it because it will give you directly acid. CrO3 fine, PCC fine. You may study that the best reagent to convert a primary alcohol into aldehyde is which one? PCC, pyridinium chlorochromate. Then, in the following reaction, what is Z? Let me practice. CH3, CHOH, CH3. It is an alcohol. This compound is X. First they undergo oxidation. All of you dear, please check it whether the given alcohol is primary or secondary alcohol. I think it is a secondary alcohol, correct? Because the OH connected carbon directly connected to 2 carbon. You know, secondary alcohol, primary alcohol on oxidation aldehyde, secondary alcohol on oxidation ketone. You make the alcohol position as a ketone. What is this ketone? Propanol. This is your compound Y. Propanol you are going to treat at the same reaction we discussed before. Propanol we are treated with which one? Methyl magnesium bromide, Grignard reagent. We studied any Grignard reagent when you treated with a ketone, your product will be a tertiary alcohol. This is very simple to write the product. You don't need to study the all mechanism. First you will get the thing, you will again adding water. Directly we can write the product. Since it is an entrance type of a question exam, MCQ exam, directly we can answer. How? You know very well, in Grignard reagent, Mg plus is there, the remaining alkyl group is negative part. Anyway, you will attack this negative part here, right? Yes or no? And this become O minus. Finally, this oxygen you will make it as OH. Correct or no? You can see the previous mechanism. So anyway, whatever the alkyl group, you will definitely add into this carbon. O becomes OH. Write it directly. Your product is ready. CH3, CCH3. The upcoming CH3, the O becomes OH. Yes. Tetrabutane alcohol. Or what is the IUPAC name of this compound? 1, 2, 3. 2-methyl propan 2-ol. 2-methyl propan 2-ol. 2-methyl propan 2-ol. Option C is the correct answer. Yes or no? Directly we can write the product like this. Okay. Now, vapors of an alcohol X when passed over hot reduced copper. So you have an alcohol X. We are passing copper, hot reduced copper. We studied now one of the catalysts like one of the oxidizing agent copper at 573 Kelvin, hot copper. Correct. This is the one. So alcohol they are treating with the copper at 573 Kelvin. It produces a alkene. Huh? We know primary alcohol on oxidation we will get aldehyde. Secondary alcohol on oxidation ketone. And tertiary alcohol, I said you, they won't undergo oxidation. Yes or no? But instead of that, in the presence of an oxidizing agent like a copper at 573 Kelvin, they don't undergo oxidation, that's sure. But instead of that, they can undergo elimination. Which elimination? Like a hydration, dehydration. Water can be eliminated. It will form alkene. Keep in mind, primary alcohol oxidation, aldehyde. Secondary alcohol oxidation, ketone. Tertiary alcohol oxidation, what takes place? Instead of that, dehydration can happen. Let me take the okay, this is not a question to answer this one. So when an alcohol, when it is a tertiary alcohol, then it will give you which one? Alkene by the elimination of water. So if you want to get an alkene, it should be a tertiary alcohol. I will show you one example. What happens when tertiary butyl alcohol? What is tertiary butyl group? This is called tetrabutyl alcohol. Is passed over copper at 300. 300 degrees Celsius equal to 573 Kelvin. I told you this is a tertiary alcohol. On tertiary alcohol, if you are using copper at 573 Kelvin, what we have to do? Dehydration. What is dehydration? OH1 you take from alpha carbon, all beta are similar. So hydrogen you take from beta carbon. Make a double bond between alpha beta. So your product is this one. What is the product name? Let me name the product. This is 1, this is 2, this is 3. So 2-methyl, right? Second position there is a methyl group. 2-methyl. The total for 3 carbon, proper 1-ene. 2-methyl, proper 1-ene is the compound. 2-methyl, proper 1-ene. 2-methyl, proper 1-ene is formed. Option B. Keep in mind, tertiary alcohol, when you treat it with the copper at 573, they won't undergo oxidation. Instead of that, dehydration. Next, which of the following reagent cannot be used to oxidize primary alcohol to aldehyde? What are the common things we are using? As already discussed, primary alcohol on oxidation, we will get aldehyde. What is the common thing we are using? Best is PCC, or we can use anhydrous CrO3, or we can use copper at 573. Which one cannot be used? Option A can be used. Option B you cannot. Option B is the answer. Why? KMnO4 is a strongest oxidizing agent. It will directly convert alcohol into acid. Okay. Pyridinium chlorochromate. Yeah, that is called the PCC. That's fine. Copper at 573. Fine. Option B is the answer. Next one, all of you. Which of the following compound will be easily attacked by an electrophile? What is this? Option A, benzene. What is option B? Chlorobenzene. What is option C? Phenol. What is option D? Toluene. Correct. Benzene with the CH3. Which is where electrophile can easily attack. What is an electrophile? Electron loving compound. What is the electron charge? Negative. So what should be the charge of electron loving compound electrophile? Positive. We know electrophile we will express by the symbol E plus. Electrophile E, the charge is plus, which means it is electron deficient compound or positively charged one. Into the 4 compound, to which one you can add this electrophile easily? That is a question. Keep in mind, all of you. In a benzene ring, electron withdrawing group can be present, or in the, it's a very important, okay, electron donating group can be present. Keep in mind, a list of electron withdrawing and donating group I have already given to you. Electron withdrawing group, if it is present on benzene ring, they will try to pull the electron from benzene ring. You studied the resonance structure, everything. While drawing the resonance structure of any electron withdrawing group on benzene ring, for example, nitrobenzene, cyanobenzene, benzaldehyde, etc., you can see that the ortho and the para positions are positive charge. What is the positive charge meaning? Electron deficient. Why electron deficient? Because electron withdrawing group, they will try to take all the electron from benzene ring. So ortho para become positive charge or electron deficient. The same way, if electron donating group present, they will donate electrons towards the benzene ring. Ortho and para position become electron rich. So now the answer is very clear where electrophile and nucleophile can attack. If I am taking a electrophile E plus, nucleophile Nu minus, where it will attack, dear student? Electrophile is a positively charged compound. They will definitely go to ortho and para position. Nucleophile is a negatively charged or electron rich compound. They will try to prefer electron deficient compound. What you understood from this point? We can confirm that if there is an electron withdrawing group present on a benzene ring, nucleophilic addition, addition is very easy. Nucleophilic substitution we can easily done on ortho para. That's depend on the compound. But in electron donating group, if it is present, maybe phenol, chlorobenzene, aniline, in this kind of electron donating group can come on benzene ring, then electrophilic substitution is easy. Electrophile can easily substitute the ortho and para position because they are rich. Now come to the answer. Here chlorine is there. I told you chlorine normally it is an electron withdrawing group, but in benzene ring it acts as an electron donating group. You know the reason because of resonance and I effect everything. Alcohol is a electron donating group. Alkyl group is also electron donating group. So confusion. Electron donating group when comes, I told you ortho and para positions are electron rich. So electrophile can easily attack, the electrophile can go to any of the point. So the confusion, which one? Definitely we can cancel benzene because it doesn't contain donating group. Next, what's the doubt? Which is the best electron donating group? They are all, that's which one can be suggested to phenol. You know the oxygen it's having 2 lone pair, oxygen it's having 2 lone pair, it can donate easily. At the same time, then you can ask the question, even chlorine contain 2 lone pair, right? 3 lone pair, right? Why it is not a best donating group? You know, chlorine actually having a withdrawing tendency because it is a halogen. But on benzene ring, you know the inductive effect, everything is competent. The resonance effect all together when you consider, it acts as a best donating group. So when you comparing electron OH group and chlorine group, OH is the best donating group. So it will give electrophilic substitution easily. Your answer is option C. Okay, so they can ask you which will undergo nucleophilic substitution faster, electrophilic substitution faster. Careful about these 2 points. Next one. Out of benzene and phenol. Okay, let me take the compound benzene and phenol. Out of benzene and phenol, phenol is more easily nitrated. Of course, correct. You know what is nitration? Nitration means addition of nitro electrophile. What is the upcoming electrophile? NO2. This is an electrophilic substitution reaction. So NO2 group, you can easily, just we discussed now the previous question. Benzene doesn't contain any special group. OH is a best electron donating group. If an electron donating group come on benzene ring, I told you the ortho and para position will be electron rich. So easily electrophile can attack. Nitration means addition of nitro group. Nitro group is coming as an electrophile. So it can goes to the compound. So what's the answer? Option A. Presence of OH group in phenol increases the electron density at ortho and para. Of course. The OH position due to resonance, you can see the negative charge. Negative charge means electron richness on ortho and para. Option is option B given presence of OH group in phenol decreases. No, it is a donating group, right? So they will increase the electron density. Picric acid is a yellow colored compound. Its chemical name is, you studied 2 reactions for the nitration of phenol. Let me revise the theory also. What is phenol chemically? Benzene with the OH. Nitration you can do in two ways on phenol. One is treating with the dilute nitric acid. One we are using concentrated nitric acid. Correct. If you are using dilute nitric acid, phenol is a ortho-para directing group. So the electrophile can, what is nitration means, as I told you, NO2 group is coming. We can welcome them into ortho and para. What is the difference between dilute nitric acid and concentrated? This is a weak nitration because dilute nitric acid cannot provide maximum amount of nitro group. Concentrated nitric acid means which contain maximum nitro group. This is a strong nitration. This is strong nitration. So what will happen, dear all? Phenol is ready here. Weak nitration, one nitro group goes to ortho position, one nitro group goes to para position. You will get mixture of ortho nitrophenol and para nitrophenol. If you are treating with a concentrated nitric acid, what happened? It is giving maximum amount of nitro group. All the ortho, all the para positions are occupied by nitro group. While naming, OH is the major functional group. So number 1, number 2, 3, 4, 5, 6. We can name the system 2, 4, 6 trinitrophenol. It's a yellow colored compound. It's also known as picric acid, right? It's acidic one because nitro group is there. It is called what? Picric acid. So what is picric acid chemically? 2, 4, 6 trinitrophenol, option B. Same way you studied bromination also. Phenol, when treated with excess bromine, you studied two type of bromination in phenol. What is that? Take your phenol. Ready? Phenol treating with which compound? Bromination also you can do two type, mild bromination and strong bromination. If you want a lesser number of bromine, use bromine in presence of carbon disulfide. Bromine in presence of carbon disulfide. So you will get two product here, same like previous case. Instead of nitro, here bromine. Ortho-bromophenol and you will get para-bromophenol. What is if you need a strong bromination, we have to use the mixture bromine water. Bromine water is a strong brominating agent. All the ortho and para positions are occupied by bromine. This is a white colored substance. And what's the name? 2,4,6 tribromophenol. Right? So the answer is, which of bromination we have to follow here? Phenol treating with the excess of bromine water. No doubt, 2,4,6 tribromophenol is the major. The major product obtained on interaction of phenol with the sodium hydroxide and carbon dioxide. Carbon dioxide relating with the phenol, only one reaction we studied, that is known as Coles reaction. Coles reaction, what is Coles reaction, dear all? We are taking phenol. First we will treat it with the aqueous NaOH. This hydrogen OH is eliminated as water. You will get sodium phenoxide ONA. Second, what we are doing? First treated with the carbon dioxide. Second, we are treating with an acid. Directly we can prepare the product. This is phenol coming back, and this side COOH, carboxylic acid. Phenol and OH group and COH together or nearby on benzene ring, it is called what? Salicylic acid, right? Salicylic acid. Or Coles reaction, it is the preparation of what? Salicylic acid from phenol. So what's the answer? Yeah, salicylic acid, option C. Correct. Then conversion of phenol into salicylic acid, just we said now. Phenol into salicylic acid conversion is called what? Coles reaction. And to salicylaldehyde, you studied a major two important naming reaction in the chapter, Coles reaction and Riemann-Tiemann reaction. Coles reaction we are using to convert phenol into salicylic acid. Riemann-Tiemann we are using to convert phenol into salicylaldehyde. So Coles and Riemann-Tiemann, option D is the correct answer. What is this here? They given a starting material as phenol, okay. First, they are treating with bromine in presence of CS2. We discussed now mild bromination. Yeah, mild bromination. If you did what happened, you will get two product, right? You will get two product. Correct. One bromine goes to ortho position. One bromine goes to para position. Ortho bromophenol, para bromophenol. What is the second reaction? Second reaction, first they are treating with a chloroform and aqueous NaOH. Do you remember? Chloroform, there is a Reamer-Tiemann reaction. You know, first you will get sodium phenoxide on the ortho position CHCl2. It is an intermediate. Then we will treat with which one? HCl along with the NaOH. You will get the final product OH and ortho position aldehyde. This is called what? Salicyl aldehyde. This is called Reamer-Tiemann reaction. So what is the product? What is X-diarol? Ortho and para-bromophenol. What is Y-diarol? Y is salicyl aldehyde. Option B is the correct answer. Next one. Identify the final product in the following reaction. What is the starting material, all of you? Phenol. Phenol treating with which one? Zinc. Alright. You know, zinc is a reducing agent. It will take this oxygen atom from phenol. It is converted into benzene. Or you studied phenol when treated with the zinc, you will get a benzene. And benzene treated with which one? Acyl chloride, CH3COCl in presence of N-hydrous AlCl3. Come on, which reaction? Friedel-Crafts acylation. Very simple, you can write the product. Take a hydrogen from benzene, take this chlorine, eliminate HCl, directly add this product on benzene ring. Okay, simply you can study like this. COCH3. Benzene with the COCH3 is known as what? What's the name we studied? Acetophenone. Acetophenone. What is the answer? What is the answer? The Y compound is acetophenone, option B. Okay, study the entire reaction thoroughly. We can crack the all kind of MCQ first. Next one. Benzoquinone. Benzoquinone as a one topic we studied in the chapter, that is called oxidation. Previous one, first step is reduction. This is reduction of phenol. Just below that in textbook you can see oxidation of phenol. Let me remind you the equation once again. Your starting material is phenol. Starting material is phenol. Phenol on oxidation, it is converted into, two lines parallel and one ketone above, one ketone below. It is known as benzoquinone. Benzoquinone. This is called oxidation. Phenol on oxidation. What is the oxidizing agent here all? Na2Cr2O7. What is Na2Cr2O7 is called? Chromic acid. Right? Chromic acid. Along with what? Sulfuric acid. H2SO. So what is the reagent? Benzoquinone you can prepare from phenol by option A. Okay? Option A. Next one. A primary alcohol, they given a formula C3H8O. They said it is a primary alcohol. Okay, fine. It is heating with a sulfuric acid. Sulfuric acid and alcohol, when you treat it, you will get a dehydration alkene. It undergo dehydration forming an alkene B. B is an alkene. Okay. B when treated with HCl, it is giving a compound C. Okay. Which on treatment with the aqueous KOH? Which on treated with the aqueous KOH? We are getting compound D with the formula C3H8O. A and DR. That is the question. A and DR. What is the relation? Whether which isomer? Let's check it. Compound number A is, they said already it is a primary alcohol. How many carbon atoms are there? 3 carbon. 3 carbon containing only one primary alcohol. What is that? Which one? Generally propanol, right? So let me start with the propanol. CH3, CH2, CH2OH. Okay. This is what? Propanol. It is treating with what? Concentrated sulfuric acid. No doubt it undergo dehydration. OH you take from alpha carbon. Hydrogen you take from beta carbon. Let's make the compound propene. Alkene is ready. Alkene, when we treated with HCl, what will happen? Markovnikov addition. H plus is there, Cl minus is there. Cl minus go to carbon with less number hydrogen, here more number. What is the product here all? CH3, CHCl, CH3, 2 chloro, propane, that is compound C. Okay, it is finally treating with which one? Aqueous KOH. Aqueous KOH means what? Nucleophilic substitution. This chlorine will remove, OH nucleophile will substitute. You will get CH3, CHOH, CH3. What is this final compound? Propan 2-ol. Come on, come to the answer. This is compound D. This is compound A. What is the relation between propan 1-ol and propan 2-ol? Position of alcohol is different, right? What is isomer is called? Position isomers, right? Position isomer, option B. Consider the following reaction. What is the reaction? Let's go. Let's crack it. This is what? Phenol. Phenol treating with the zinc dust. I already told you zinc will go with the oxygen. You will get benzene. Okay. Benzene treating with which one, dear student? Methyl chloride along with the anhydrous AlCl3. What is the reaction? Friedel-Crafts alkylation. So if you take one hydrogen here, one chlorine, it remove HCl, the CH3 electrophile you can add on benzene ring, you will get toluene. Toluene they are treating with what? Alkaline KMnO4. What is the duty of alkaline KMnO4? It is the strongest oxidizing agent. You know, here what we want to oxidize, right? Let me tell you one point. Whatever the number of carbon atom on benzene ring, if you treat it with the alkaline KMnO4, the strong oxidizing agent, it will give you the final result, carboxylic acid. Whatever the carbon, for example, here you have toluene, right? Here you have toluene. Suppose you have a ethyl benzene, means CH2, CH3. Whatever compound you treated with the KMnO4, final product will be benzoic acid. You no need to depend on the carbon atom, how much carbon atom present on benzene, all of them converted into a single carboxylic acid. Okay, so keep in mind. So what is your answer, dear student? As compound number Z, that is benzoic acid. Option B is the correct answer. Next one. You can see column 1, they given so many reaction. On column number 2, they given the name of the reaction. Let's match it. All of you very carefully. This is what? Phenol. Phenol treating with what? Methyl chloride in presence of anhydrous AlCl3. Addition of a haloalkane in presence of anhydrous AlCl3 is called Friedel-Crafts alkylation. Right? Friedel-Crafts. So this is A. Next one. This is phenol again. Phenol treating with the chloroform and NaOH. Dear student, phenol treating with the chloroform. Riemann-Tiemann reaction. Your product is salicylate aldehyde. Riemann-Tiemann. This is B. And the C option, C compound. Phenol treating with the NaOH and carbon dioxide. Phenol, you keep it like this. Phenol, when they treated with the NaOH and the chloroform, it is Riemann-Tiemann. When phenol treated with the carbon dioxide and NaOH, that is Kolb's reaction. You will get salicylic acid. Salicylic acid, this is C. And last one, what is happening here? All this is salicylic acid treating with the NaOH and calcium oxide. This actually we studied in 11th grade. NaOH and calcium oxide mixture is known as, you may study that, soda lime. Soda lime, right? Soda lime. Soda lime. It is a decarboxylation. You know, this carbon dioxide part is eliminated, right? This side. So this is called what? Decarboxylation. So what is your answer here all? A with the 2. A with the 2, that is only one answer, the B option. Right? Then, ethers is obtained from ethyl alcohol in the presence of H2SO4 atom. In the ether topic in textbook, you can see first ether preparation. Let me take ethanol as an alcohol. You know, ethanol, when you treat it with a concentrated sulfuric acid at a 443 Kelvin, no doubt it will undergo dehydration. What is dehydration? OH you take from alpha carbon, one hydrogen you take from beta carbon, you will get alkene with the water. The same alcohol, when you treated with the same reagent concentrated sulfuric acid at 413 Kelvin, here 443, here 413. If you just change the temperature from 443 to 413, your product is entirely different. Instead of getting an alkene, you are getting an ether. Which ether? CH3, CH2, one ethyl group left side, one ethyl group right side, and there is an oxygen at the center, ether. So if you want to prepare this ether, you have to alcoholize it. That's it. So what ethers you can obtain from ethyl alcohol or ethanol at what temperature? Okay, 413 Kelvin. Ethers are prepared by the reaction of sodium alkoxide and alkane halide. You know, Williamson synthesis. When a haloalkane treated with the sodium alkoxide, what will happen? Sodium halogen will eliminate. You will get ROR ether. This is called Williamson ether synthesis. Okay. What is the question here all? Which of the following reagent would be taken to prepare? We want to get this ether. Which ether? Methyl tert-butyl ether. What is methyl group? This one. What is tert-butyl? One carbon with the 3CH3. Methyl tert-butyl ether. We want to prepare. In order to prepare this ether, which all haloalkane and sodium alkoxide we want to choose it? Any haloalkane and sodium alkoxide if you are using, you cannot remove sodium and halogen, you cannot prepare sodium. Okay? Let me tell you a simple idea, a simple clue. What is this reaction called? Williamson synthesis, right? Preparation of ether is called Williamson synthesis. What all things we are using in Williamson synthesis? This is a alkyl halide. What is this is called? Sodium alkoxide. Sodium alkoxide. If you want to eliminate sodium and halogen to prepare ether, you do something or you do special in this point. Your haloalkane should be a small group. Okay? Remember like this. Your haloalkane should be a small group. Sodium alkoxide should be a big group. Why? Here all, we studied that already, no need of explanation. Anyway, even one student are there not knowing the concept, let me tell you. If you want to perform Williamson synthesis, you make sure that your haloalkane is a smaller group, sodium alkoxide part is a bulky group. Then you can take sodium and halogen, eliminate, mix it. Fair. Or ether you will get it. You know, big, if it is the sodium alkoxide group, it can act as just a nucleophile. It can act as just a nucleophile, so normal substitution will happen. But if the sodium alkoxide group is a smaller group, for example, NaOCH3. So what is the nucleophile forming here? This is the Na plus and O minus. This is the nucleophile. That is not a nucleophile. Not only a nucleophile, it is a strong base also. If your sodium alkoxide part is a smaller group, the base form, the nucleophile is act as a very strong base also. In the presence of a strong base, haloalkane will undergo elimination, beta elimination. You know, during beta elimination reaction, what is a common reagent we are using? Alcoholic KOH. Correct? In the presence of a strong base, a haloalkane, instead of undergo Williamson synthesis, they will undergo beta elimination. So if you want to get ether, if you want to perform Williamson synthesis, your haloalkane should be a smaller group, sodium alkoxide part should be bigger. Let's go. Option A. Can we choose option A? No. You may think this bromine and sodium we can eliminate, we will get this ether. No, I told you here sodium alkoxide part is a smaller group. Smaller group. If it is smaller one, what happen? It can act as a strong base. Okay? It can act as a strong base. In the presence of a strong base, this haloalkane will undergo beta elimination instead of ether preparation. So first one is not possible. Second one possible? Yes. Because in second one, your haloalkane part is a smaller group, sodium alkoxide part is a bulky group. That's not enough. The group should be matching. Let me check. CH3Br is given plus NaOC CH3 CH3 CH3. The condition is matching or not? Your haloalkane part is a smaller group, sodium alkoxide part is a bulky group. What is a nucleophile here? The whole big group. It can act as only a nucleophile, not a base. Okay, such a cases, NaBr eliminate, mix the remaining alkyl group with oxygen, you will get ethyl tertibutyl oxide. Okay, so answer is option B. Complete the missing link. The first one is given CH3CHBr, single bond CH3. It is treating with the alcoholic KOH. What we have to do? Alcoholic KOH means beta elimination. Bromine you take from alpha carbon, one hydrogen you take from beta carbon, make a double bond between alpha beta, propene is ready. This is your compound X. This is we are treating with what? HBr. Very careful, peroxide is there or no? Yes, peroxide is there. We have to follow anti-Markovnikov rule. H plus is there, Br minus is there. Anti-Markovnikov rule means negative part to carbon with the more number of hydrogen, positive into less number of hydrogen. So CH3, CH2, CH2, Br. So compound Y. This one we are treating with the what? This one we are treating with the which one? NaOCH3. So you may think here also beta elimination. No, here all are smaller groups, right? Here haloalkane is a smaller group, even sodium alcohol is a smaller group. Such a cases directly we can proceed. NaBr you can eliminate, you will get either CH3, CH2, CH2O, CH3. This will be the ether. So this is your compound set. Where you can identify X, Y, Z. X is propene, Y is 1-bromopropane, and the last one is OCH3. Yeah, option D is the correct answer. Next one. Ethers having lower boiling point compared to their isomeric alcohol. For example, if you take this is called ethanol. With the same formula, I can prepare an ether methoxymethane. You know why alcohols having highest boiling point? You know, alcohols are connected through very stronger intermolecular hydrogen bonding. Stronger the bond, high boiling point. Such hydrogen bonding is not possible in ether. So what is the answer? Option A. Hydrogen bonding in alcohol that is absent in ether due to low polarity. Yeah. Alcohols are connected through very strong hydrogen bonding. Stronger the bond, high boiling point. Which of the following are the products shown by the reaction of methoxyethane with the hydrogen iodide? What is methoxyethane? CH3O ethane, CH2CH3, methoxyethane reacting with the hydrogen iodide. A simple trick let me give you, dear student. On the oxygen atom, left side a primary group, left side a primary, secondary group, left side secondary, primary group, left side secondary, right side secondary. In these cases, when comes, you try to break. You know that this is actually Hi containing H plus and I minus ion. Correct. Same ion, same. We need a ion in ether also. Then only we can react. So in order to get an ion, either this carbon-oxygen bond or this carbon-oxygen bond need to break. But which? That is the question. So that's why simple idea let me give you. If on the oxygen atom, these groups comes, then you try to break the less crowded or less steric hindered CO bond. Less crowded. For example, let me give you a clue for that. I'm taking a compound CH3, CH2, O, CH2, CH3, CH3. Suppose this is the ether I am giving. Okay, the left side there is a ethyl group, right side there is a isopropyl group. Which CO bond you want to break it? The left one or the right one? If you look into the left part, it is primary, correct? Because this carbon connected to only one carbon, it's primary. Right one, this carbon connected to two carbon atoms, secondary. So this belongs to this category. In such a cases when comes, if all these four cases when come, the less crowded part CO bond, you break it. Which is the less crowded part? We can say this CO bond. You have to break this CO bond. The less crowded part, we have to break it. Because left side only 2 carbon, right side 3 carbon. If you break those carbon atom, we will get this carbon, oxygen always negative because it is highly electronegative element, carbon will get positive. Understood? So any of this group, any of this pair come, where is the less crowded area, you break that CO bond. Fine. Because they follow SN2 mechanism. These system follow SN2 mechanism. What is SN2 mechanism? The less steric crowded part reaction will take place fast. Now it can be another situation. What is the other situation? The other situation is not only primary, secondary, right? Tertiary can come. When tertiary group along with a primary, a tertiary group along with a secondary group, something when comes, no doubt dear all, break the tertiary part. Break the tertiary part. Because it follow SN1 mechanism. SN1 mechanism to better to get tertiary carbocation greater. Okay, this is the one, SN1. So let me come to this question. In this question, you can see on the oxygen atom, left side only primary group, a small carbon, right side also a primary group. When primary when comes, we have to follow SN2 mechanism, break the less crowded CO part. Which is the less crowded? This one. So oxygen minus CH3 plus. Now you interchange the ion. To the CH3 plus ion, we can get ion. And the right side we will get CH3CH2OH. This is the product you are going to get here. So what is the product we can say? CH3I and CH32H5OH. Option D is the correct answer. Alright. The next one, in the following reaction, I think it's given here a benzene with the OCH3. Benzene with the OCH3 is known as what? Anisole. It is going to treat it with which compound? HBr, right? HBr. Here which one we need to break it? This is an aromatic type ether. Benzene is there, OCH3 is there. Here I given two cases. One, this category where you want to break. Second, tertiary group come where you want to break. This is another one, a aromatic type ether. In aromatic type ether, if they given here all, you should break. After the breaking, you should get phenoxide ion. So I want to break this one. What is this species? This species is called phenoxide ion. You just ensure that after the breaking the CO bond, you are getting a phenoxide ion. Okay, so I can do that. What here? This is the phenoxide ion and CH3 plus. Correct. So I want to, if I want to get phenoxide ion, this bond or this bond, which one I want to break? This bond I want to break. Then I will get phenoxide ion here, CH3 plus here. Now you interchange here H plus and Br minus. So on the phenoxide ion, I will get H1 and CH3 group I will get Br. So what is your answer? C phenol and CH3Br, that is in option D. Understood? Then anisole on reaction with, what is mean by anisole? Benzene with OCH3. Benzene with OCH3 is called anisole. Anisole on reaction with the chloromethane. What is chloromethane? CH3Cl in presence of anhydrous AlCl3. What is this? Friedel-Crafts alkylation. Which alkyl group is coming to benzene? CH3 plus. Electrophile, right? Where the electrophile can attack, that is depends on the existing group in benzene. What is the existing group in benzene? Alkoxide, methoxy. I given methoxy group is an electron donating group. Electron donating groups are ortho-para directing group. So ortho-para. So CH3 group can goes to ortho position and the para position. Okay, so this is the one. Ortho position 1 CH3 group, para position 1 CH3 group. So what is the product here? Ortho-methyl anisole, para-methyl anisole. Ortho-methyl anisole, para-methyl anisole. Option C is the correct answer. Next one. What is the correct order of the reactivity of the alcohol in the following reaction we discussed before? This is a normal alcohol. What is this mixture, dear student? HCl with the zinc chloride is known as Lucas reagent. We know Lucas reagent test is most given by tertiary, then secondary, then primary. So the reactivity order is option C, Lucas test. Monochlorination of toluene. You know toluene. What is toluene? Benzene with the CH3. Toluene in sunlight, okay, chlorination. What is chlorination? Addition of Cl2 in sunlight, okay. In haloalkane video, we clearly discuss what happened, what are the two type of chlorination possible in toluene. When toluene treated with the chlorine in presence of light, you know, light means free radical substitution will take place. The chlorine you should add on the alkyl group, not in the benzene ring. So chlorine, one of the chlorine you can add on this carbon. So the product will be what? Benzene with CH2Cl. Benzene with the CH2 is known as which group? Benzyl chloride, right? Benzyl chloride. Okay, note over. Followed by hydrolysis by aqueous KOH. This compound we are treating with which one? Aqueous KOH. What happened when we treated with the aqueous KOH? The chlorine is removed, OH minus nucleophile will substitute. We will get benzyl group with one alcohol. What's the name? Benzyl alcohol. Option first one, benzyl alcohol will be the major product. Understood here all? Okay, so these are the part 1, around 50 questions for the chapter alcohol, phenols and ether. So we will meet again in the second video with part 2 for the same chapter, the most important question, alcohol, phenols and ether. Okay, so we can meet in the second video again. Thank you.